In this video, we're going to look at what happens when you need to add the terms of a geometric sequence, which is what we call a geometric series. Now, as a quick reminder, a geometric sequence is something created by a formula like this, where we have 2 being raised to a power. And if we plug in numbers k equals 1, k equals 2, k equals 3, what happens is it creates this pattern of numbers where I can see that they're multiplying by 2 over and over and over again to go from one term to the next. That's what happens when you have a number being raised to a power. That means you're multiplying by 2 over and over and over again based on whatever the exponent is. Now, that's what creates the geometric sequence, but what we're going to focus on in this video is what happens if we need to add those terms together. That's what we call a geometric series. So here is our formula for the geometric series. Now, I will mention that there are actually going to be 2 formulas in this video. This first one is going to be when you have a finite number of terms. So later on, we're going to look at what happens if you have an infinite number of numbers to add. There is actually a way that you can get an answer sometimes. But for right now, we're going to talk about what happens if you only need to add 10 or 11 numbers. Geometric series usually do not have as many terms in them as arithmetic series do, because when you keep multiplying by 5, it doesn't take long to get to a number that has like 30 digits in it. So usually you're dealing with smaller numbers of terms for these. So what do we need to know for this formula? We need to know the first term in the sequence. We also need to know what is the common ratio, which means what number are they multiplying by to go from term to term. That gets used twice, actually. And we need to know how many terms there are in the pattern altogether. Now, one nice thing about this formula is we don't need to know the last term in the sequence. They might have given it to you, but it doesn't actually get plugged in anywhere. So now let's talk about a couple of the examples. So the first thing I see here is I notice that this is a multiplying pattern. If I multiply by 2, that goes from one term to the next. So that means r equals 2 in this case. Next, I see that we have our a sub 1 value. The first term in the pattern is 3. We do also know the a sub n value, but that's not really going to help me in this problem. Not for the sum formula anyways, but it will be something that I need to use for a different value, because they did not tell me how many numbers I have in total. So we're going to need to solve for n. Now, to do that, we're going to use the explicit rule for a geometric sequence first, so that we can figure out how many numbers there are here. And the formula for doing that is going to be the a sub n equals, and then it's going to be the first term, which was 3, times r to the n minus 1 power. So this is the explicit rule. This is not the rule I was just showing you a moment ago. Now I need to solve this formula for n. So my first step here would be to divide both sides of the equation by 3. And so if I divide by 3, that would give me 256. And then this technically can be solved with logarithms. However, I think an easier way to generally approach this is to see if you can rewrite both sides using a common base. So that was something we talked about back on the logarithm unit. And in this case, if you know that 256 is a power of 2, you just need to find out 2 to what power equals that number, which allows me to rewrite 256 as 2 to the 8th power. So I've rewritten both sides using a common base now. And the advantage to this is it lets you set the exponents equal. So now I can just write 8 equals n minus 1. And if I add 1 to both sides of the equation, now I know that there were 9 numbers in total. Now, that wasn't a very big number, so I probably could have figured it out if I just kept applying my multiply by 2, multiply by 2, multiply by 2 rule. But there might be cases where this is a very big number, and I want you to know how to get around having to list them all out and multiply them over and over and over again. Next, now we actually have the information we need for using the sum formula. So I'm going to be writing s sub n equals, and then it's the first term in the sequence, times 1 minus r to the n power over 1 minus r. So this is something that can be calculated. It can be a little bit obnoxious, especially when you have big numbers like 2 to the 9th power. So you might want to use a calculator for some of this. In fact, I already did some of the calculations here, so I'll use my post-it note for reference. So when you're calculating this, you would probably first want to plug in what is the 2 to the 9th power, and then do 1 minus that number. So you should get negative 511 from that step. Now on the bottom, this part's pretty easy. 1 minus 2 we know is negative 1. For your next step, you would multiply 3 times negative 511, so that should give you negative 1533. And dividing by negative 1, we don't want to write it that way. We just want dividing by negative 1 to remind us that we need to flip the sign of our answer. So my final answer here would be a positive 1,533. So that's the sum of all of those numbers if I added them up. Let's look at a second example. So this example is a little bit different. This time, they've given me the n value. So now I know n is 9. So I have 9 numbers in total. They've given me a sub 1. So I know a sub 1 is negative 1. And I need to be able to figure out what r is. What are they multiplying by to go from term to term? So you can pick a number and divide by the number in front of it. It doesn't matter which one you pick. Divide by the number in front. You should see that r is equal to negative 8 in this case. Okay? Well, once we have these three values, if you look back at the formula, remember we only need to know a sub 1, r, and n. So in this case, we actually have everything we need, which means we're not going to have to use the explicit rule first to find the rest of the answer. So I can go straight into the sum formula, but it is going to be a bunch of ugly numbers in this case. So when I'm writing this out, I'm going to have my first term in the sequence is negative 1, and then it's 1 minus r to the n power over 1 minus r. Now you need to be very careful when your r value is negative, because if you're typing this into a calculator, you need to put parentheses around the negative value, or your calculator is going to give you an incorrect answer when you raise it to this power. So being very careful and meticulous about these calculations, I'm going to treat this as negative 1 times 1 minus, and I would recommend just evaluating what is negative 8 to the 9th power. In this case, I got that it was negative 134217728. It's a very large number because negative 8 raised to the 9th power, multiplying negative 8 over and over and over again gets very big very quickly. On the bottom, when you subtract a negative, that's just the same as adding, so I can make this 9. Now right here, I'm trying to avoid doing too much at the same time, but I just have 1 minus a negative number. So again, I can just think of this as 1 plus this number. So I'm going to write this as negative 1 times, and then this will end up being 134217729 divided by 9. Now these last two steps aren't too bad. So I need to multiply by negative 1, which is basically just going to flip the sign of my answer, but I do also need to divide that number by 9. So if we make our answer negative, and if we divide this number by 9, what you should get in total is negative 149,130,81. But you would definitely want to use a calculator for doing some of these answers. Now the good news for you is that the finite geometric series are actually the harder ones to solve. We're going to look at the infinite ones next. Here's the formula for the infinite geometric series. So this one actually has a much simpler formula to use. You only need to know the first term in the sequence, and you need to know what r is. But there's a requirement for you to be able to find the sum. And the requirement is listed here. You can only find the sum of an infinite geometric series if and only if, that means the only time you can do this, is the r value is, the absolute value of r value is somewhere between 0 and 1. So we need it to be a fraction or a decimal, like 1/2 or 1/3. So what has to be happening is it has to be that you're multiplying by a number that's making your successive terms get smaller and smaller and smaller. And eventually what happens is the terms get so small that they're so close to 0, they're not really adding anything to your sum anymore. That's kind of the idea behind this. So make sure you check this first. Is the absolute value of r less than 1? If it is, then you can plug into this formula, and it usually goes pretty quickly. So here's an example. If I was looking at this, I would recognize that my a sub 1 term is 2, but more importantly, I want you to notice that my terms are multiplying by 3. So since r equals 3, do I have the situation where the absolute value of r is less than 1? No, I do not. Absolute value of 3 is not less than 1, so I cannot use the infinite sum formula. So there's no finite answer on this. I wouldn't be able to find the sum, basically. So that's the quickest possible situation you would have on these examples. Let's talk about one where you actually can find the sum. This time, I have a sub 1 equals 10. And this time, I notice that if I pick a number and divide by the number in front, what's happening is I seem to be dividing by 2. So 5 divided by 10 gives me an r value of 1/2. So what's happening is I'm multiplying by 1/2 to go from one term to the next. Is the absolute value of 1/2 less than 1? Yes. This time I can use the formula. That's good. So this time I can go ahead and write that s sub n equals, and it's the first term over 1 minus r. So this one's a lot easier to work with. You don't have as many exponents or anything to deal with. That's what makes the other one so hard. Well, 1 minus 1/2 is just 1/2. And then don't forget that instead of dividing by 1/2, you can multiply by the reciprocal. So instead of thinking of it as divide by 1/2, think of it as multiplying by 2. So this would just be the same as 10 times 2 over 1, which equals 20. So if I added these numbers up, what happens is eventually the numbers get so small, I'm adding numbers like 0.00000001, it ends up not really affecting the total sum. So the infinite sum in this case is 20 if I was able to add those numbers for the rest of my life. And that's it for the lesson on geometric series. Just make sure you remember to check the R value for the infinite geometric series first. It needs to be less than 1. The absolute value of it needs to be less than 1. And for the finite ones, it is a little bit more tedious. Definitely expect to use a calculator when you're dealing with all those big exponents because those numbers get very big very fast. And that's it for the lesson. Thank you.